Hi, my name is Gabe. I'm a mathematician and a tutor, and I'm excited to work with you all on hypothesis tests today. Today's topic will see us apply the general hypothesis test method to a difference in sample means for two populations. We will begin by doing a quick overview on the general structure of a hypothesis test. We will then discuss the specific form that the test statistic takes on for the difference of two population means. Determining such a test statistic is, generally, the most distinct part in performing a hypothesis test for each different population parameter, so this is very important. Finally, in order to solve the problem, we will discuss how to determine an appropriate p-value from the student's t-distribution in order to get to the final stage of the hypothesis test. Let's see how this works in the context of an example hypothesis test. Scientists are attempting to study whether a mouse will move through a maze faster if they have recently been given cheese. In any scientific experiment like this, the basic assumption is that the two groups will perform the same. That is, scientists have to assume that the mean difference in run times between the mice with and without cheese, written as mu d naught, is 0. While the d subscript refers to the difference in means, the naught subscript indicates that this is the proposed null value for the difference between the two runs. In this video, the black mice will represent the mice running through the maze without cheese, while the orange will represent the same mice running through at some later point, having been given some cheese. The experimental data may demonstrate that the average times are in fact different. Perhaps mu1, the runtime for the black mice, may not be equal to mu2, the runtime for the orange mice, where these variables refer to the true population parameters. In this case, mu d, which is equal to mu1 minus mu2, would not be equal to 0. This test, where we are trying to determine whether or not there is a statistically significant distinction between the two population means, is setting us up for a two-tailed hypothesis test for paired population means. Let's see how we can fit this problem into the general structure of a hypothesis test. A hypothesis test in general consists of 5 stages. In the first stage, we construct the null and alternative hypotheses. We then have to calculate a test statistic. This test statistic is a way to take the data at hand and compare it to some underlying possible statistical distribution, which can tell us whether the observation is likely or unlikely. For this problem, we will be calculating a t-statistic. In general, the test statistic is equal to the sample statistic gathered from the collected data minus the null value of the population parameter, all divided by the standard error of the problem. The standard error will be related to the underlying distribution of the problem and the dataset sample size. We will discuss the particular form for this difference of paired population means today. In the third stage of the test, we use the calculated test statistic to calculate a so-called p-value for the observation. The p-value gives us a single number against which to compare how likely it is that our event could be attributed to random chance. For this test, we will refer to the student's t-distribution to determine this p-value. In step 4, the p-value calculated at stage 3 is compared to a threshold of statistical significance, which is determined at the beginning of the problem. Finally, in the last step, we accept or reject the null hypothesis based on the threshold of statistical significance. Let's go through these steps one at a time in the context of our example problem to see how it all fits together. In our first step, we have to determine our null and alternative hypotheses based on a research question. Recall from our setup that we want to know whether or not there is any difference between two populations, which would give us a mu d naught of 0. Our general research question is whether or not there is a difference in maze times for the two populations. This would make our null hypothesis that there is no difference in maze run times. Mathematically, this would be written as h naught colon mu d is equal to 0. Essentially, we are stating the null hypothesis that the population parameter for the difference between populations is 0. Since we are trying to investigate whether or not there is any distinction between the two populations, our alternative hypothesis for the two-tailed test is simply that there is some difference in maze run times across the two populations. Mathematically, this takes on the form of ha colon mu d is not equal to 0. Finally, we determine a significance level at which we will accept that the gathered data represents a true deviation from the null, rather than something that we can attribute to chance. Commonly, this level is set to 5%, and we denote the significance level as alpha equals 0.05. The relevant information that we need to continue on from this slide are just the equations in black, but we will come back to the written out hypotheses in the last step of the process. In summary, for stage 1, we have our null hypothesis that the population parameter for the difference in population means is equal to 0, and an alternative hypothesis that mu d is not equal to 0. We will do this test at a significance level of 0.05. This sets us up for step 2, the calculation of the test statistic. The basic form of the test statistic was mentioned before and is equal to the sample statistic minus the null value divided by the standard error. In the specific case of the difference in population means, our test statistic will be a t-statistic, our sample statistic will be d bar, or whatever the difference in the population averages when we summarize the sample data, and the null value is simply 0. Finally, the standard error associated with the d bar will be equal to the standard deviation of the sample data divided by the sample size of the sample dataset. Let's provide some data for our problem and pull the statistic together. Keeping in mind that our null and alternative hypotheses and the significance level for testing, let's say that over 21 trials, our mean time for the black mice who have not been given any cheese is 26 seconds. Our mean time for the orange mice, who are the same mice just given some cheese before their run, is 30 seconds. This gives us a sample difference of -4 seconds. Finally, both standard deviation for the difference in paired observations, SD, is 12 seconds. From here, we can calculate the test statistic for the equation derived earlier. That equation is, again, t equals d bar minus 0 divided by the standard error, which is itself equal to the standard deviation of the differences, divided by the square root of the sample size. Plugging in our relevant variables, we have -4 minus 0 in the numerator and 12 divided by the square root of 21 in the denominator. This returns a value for t of -1.53. Before we get into the next step of the problem, stop for a moment to think about whether it is unreasonable for us to have a negative value for our t statistic. Keep this in mind as we begin to discuss step 3, as we determine the p-value which corresponds to the test statistic from the student's t-distribution. One crucial aspect of the student's t-distribution is that we must consider that it varies with the degrees of freedom of the dataset. Thus, to get a relevant p-value, we must determine the degrees of freedom in our dataset. For the paired population mean t-statistic, the degrees of freedom, abbreviated df, will be equal to the sample size minus 1. Specifically, that gives our problem 20 degrees of freedom. Now that we have our degrees of freedom, we need to go determine the p-value for a t-distribution with 20 degrees of freedom, a t-score of -1.53, under a two-tailed test. This graph provides a t-distribution with 20 degrees of freedom. Because this is a two-tailed test, the p-value corresponds to the total area to the right of our t-score is a positive number, and to the left of our t-score is a negative number. For our t-score of -1.53, we have that the shaded area on the graph to the left of -1.53 and to the right of 1.53 each have an area of roughly 0.071. This leads to a combined p-value of 0.142. This is why it was okay for our t-score to be negative earlier. We specified that we were working with a two-tailed test, so we need to use the positive and negative values for our t-score to determine this area. At this point, having used the sample data to determine the test statistic and then that to determine our p-value, we are ready for step 4, where we perform a statistical significance evaluation. For this, we must look explicitly at the significance level alpha and the p-value. Recall that the p-value represents the proportion of times when the observation's deviation from the null could happen by chance. If the p-value is smaller than the significance threshold, then this threshold provides us a level of certainty that the observation was not due to random chance. So, by now, we just have to ask the question of whether p is less than alpha. Plugging in both values, we ask whether the inequality 0.142 is less than 0.05 holds. This is false, leading us to step 5, where we either accept or reject the null hypothesis. Since our threshold evaluation was a false inequality, we have to accept the null hypothesis. In terms of our original framing, this means that we have to eliminate the statistical claim of the alternative hypothesis and stick with the null. This leads to the conclusion that at the significance level of 5%, the data does not support any difference between performing the runs with and without cheese. This may be confusing because we did report a difference of 4 seconds during the trials. Still, the hypothesis test, with its p-value of 0.142, suggests that this could have happened by sheer chance 14.2% of the time, so the difference is not statistically significant at our threshold. This type of conclusion is key to a good hypothesis test. Hypothesis tests are designed to filter out noisy results and only allow for significant conclusions. Yes, there was an observed difference across the two populations, but not significant enough to be valid at a 5% level. Some science experiments, such as those in particle physics, have a threshold significance level of 1/10,000th of a percent. Over the course of this lesson, we have reviewed the general structure of hypothesis tests. We then introduced the test statistic formula for a two-population mean difference. And finally, we used an example scenario to walk through a full hypothesis test for a two-population mean difference population parameter. This included finding the proper p-value and testing against the significance level. Thank you for working through this hypothesis test sample calculation with me. For more specific practice on other sample statistics, Chegg has a series of videos available for you to find out more.